All right, good afternoon. Thank you for attending this webinar, Multiple Solutions for our RSK175 Analysis, put on by Teledyne Techmar. We are recording this webinar. It will be available along with the slideshow presentation on our website. My name is Nathan Valentine. I am the Applications Manager here at Techmar. Actually, a lot of the data that's going to be presented in this webinar, I did the majority of the analysis, so if you have any questions, you can post them in the chat at any time, and we'll try to save some time at the end to answer as many as we can. So if we do go over, feel free to stay, and I'll try to answer as many as I can. If not, then I will try to get a response back to you as soon as I can. We're going to spend maybe the next 45 minutes or so talking about RSK175, dissolved gas analysis in water, and a couple different variations on the technique, and kind of where we see things going from here. All right. So here we go. We're starting with the hydraulic fracturing and dissolved gas analysis. We're going to talk about this because it's really, if you've paid attention to the news at all lately, it's all over the place. Started off in Pennsylvania, but it's worked its way across the majority of the United States so far. So hydraulic fracturing, the drilling process, we'll talk in a little more detail exactly what it does, what it entails, and the impacts on it. We're going to introduce a couple of existing methods that are used, the headspace methods used to do the dissolved gas analysis, as well as a new PURGE and trap method that we developed here at Techmar. So what is hydraulic fracturing? It is a drilling process that they use to recover methane, ethane, any of the natural gas components from pretty difficult matrices in the ground. It's strictly for like coal beds and shale formations, and it's become more and more prevalent as technology has sort of allowed high amounts to be recovered from these sort of processes that are really relatively old. Hydraulic fracturing has existed for about 60 years. It just now becomes, the technology has come to the point where it's cost effective with the price of oil and other commodities, that it's become more and more cost effective to do it this way. It involves injecting high amounts of water at high pressure with sand and other chemicals to break up the shale where the gas is actually trapped underground, and then the backflow of the water back up to the well will actually, they collect the methane and then other natural gas components from there. And it's becoming increasingly more popular, and in one projection I've read that it's going to become nearly 45% of the nation's total natural gas supply by 2035. And it seems to be, with some of the operations that I've heard of, it seems to be growing exponentially. And this slide, I know we've used it in a couple of our application notes. It kind of gives a good overview of exactly how the process goes. As you can see, they drill a well, and then they hit the shale layer, and then they'll actually bore horizontally along the shale, which will create a bunch of micro cracks. And then they'll send a boring tool down that will actually perforate the casing, and then through that casing, all those little holes, they will actually inject like a chemically treated water and sand that will push the fractures open and release the gas from the rock. And then as they pull that back up to the well, they can divide it out from the water, and then you get all your different natural gas components that they can then package and sell to whoever. It's kind of interesting. It's not super complicated. It's just a really effective way of getting these natural gas components out of the ground. But that kind of explains a little bit more detail. People aren't real familiar with it.
We're having some sound difficulties. I'm sorry to interrupt. I just wanted to make sure. It sounds like we might be having some difficulties with the sound. So we're just we're checking to make sure that everything's okay. So I'll let Nate continue, but if some of you can't hear, we're checking on it on the other end.
Okay. Well, this slide shows sort of where all the shale gas, where they're doing it, where potentially they're going to be drilling. These are all the shale plays in North America that have been mapped out. Might be familiar with the Marcellus shale. This has getting a lot of press because of in the area of Pennsylvania where it seems that a lot of the regulation has come from. But there, as you can see, it's all over the United States. So it's not just a regional issue. It's not going to this impact is not going to be regional. It's going to be across the whole United States, and actually, it's even used in parts of Europe. So it's going to be, and it continues to be something that people are going to be doing. So it's going to have an impact across the globe. Here's a slide. I don't really want to spend too much detail on this. This is kind of just an overview of the chemicals that are used when they inject. When it's chemically treated water, these are sort of the chemicals you're dealing with. Majority, it's 99.5% is water and sand. So mostly water and sand to kind of push the fractures apart. But these other components are kind of like I said, I won't go into detail on what they do, but these are the sort of things in there that they have functions specific to the process of kind of keeping things moving. And like it says, corrosion inhibitor. There's just different chemicals that are used to kind of that seem to be in blends that these companies use to do this drilling. A good reference is fracfocus.org actually has a list of these type of components and what actually chemicals they use. And it's a really good resource to use if you're interested in exactly what kind of stuff they're going to be dealing with. Potentially, if you're going to be testing any of these waters, or if you're going to be doing any of this sort of drilling, it's definitely a good resource to have. Okay, this is sort of I got to preface this slide. These are just sort of reasons that these are sort of the issues that people come up with, the reasons why we should have regulations in place, why we shouldn't do hydraulic fracturing. So I just want to say that this is not my point of view. This is not TechMar's opinion or any way, shape, or form. It's just the sort of issues that are out there and most prevalent, and I'm going to kind of touch on those and how they apply to what we have done here. There's potential public drinking water and environmental impact based on if anybody's seen the Gasland videos or heard about the flammable, the methane gas coming out of your tap water and they can light it on fire. That kind of freaks people out. It's understandable, but that's kind of where the people have made assumptions based on those videos on what happens associated with the drilling processes. So we'll touch on that. You have the air emissions and pollutions. Actually, I found this interesting. Methane is actually a much more effective greenhouse gas than even CO2 is. So people are anxious about that with sort of the impact of the emissions, extra emissions that this drilling process is going to have. You have the potential for also the chemicals that they're dealing with. Can they leach into the groundwater? Is there going to be spills? There's got to be sort of protocols to deal with that. And this is another sort of thing that's been in the news that I'm not sure if people may or may not have heard of. The earthquakes that have occurred in eastern Ohio, in the Youngstown area actually, that were actually tied to, the state has said they were tied to some faulty wells that were actually drilled along a fault line that caused some grief with the earthquakes. But that's definitely something people are definitely worried about there. Like I said, the chemicals leaching the aquifers, there are some potential things. There are glycols that are used or other things, and people are worried about them getting into the water supply. Okay, I think this slide seems to be overlapping on my screen, but this is supposed to say water usage. Water usage, these wells can use a lot of water, and in some places where water is relatively scarce, or maybe in areas like Texas where the water supply maybe couldn't handle this extra burden on the resource, could be something that might affect some of the people's opinions on the hydraulic fracturing process. And then this has mostly been, again, I apologize if it seems to be overlapping on my screen and it may be on yours, but this is supposed to be, this is mostly driven by state regulations so far. The EPA is doing an evaluation right now, but they expect to have things in place by 2013, 2014, but the states have been charged with sort of mandating any rules as far as standardization, and specifically in areas like Pennsylvania, where the Department of Environmental Protection has sort of led in trying to get some sort of standard procedures in place to kind of monitor these things. And then the last thing is supposed to say rapidly expanding infrastructure. In some of these areas, there's not a lot going on. Like in areas of Wyoming and areas in Montana and things where they're doing a lot of this stuff, there's not a whole lot of housing, and there's a massive influx of people. I actually have my in-laws live in the Youngstown area, and they actually told me a story last time that I saw them, that that was an area that originally, if you know anything about Youngstown, they used to be a big steel area, and it's kind of in the Rust Belt now, where that industry has kind of moved on, and they've kind of had, the economy's definitely hurt them recently, but now they have this huge influx of people that are coming that are setting up these drilling sites, and that are kind of trying to get all these things situated in order to do this hydraulic fracturing, and they just don't have the restaurants, the housing, the hotels and things to kind of accommodate these people. So they have people, there's like trailer parks that are specifically, these people are sort of have been designated to live in, because it's just, the infrastructure is not there yet. And so there is a burden on the local economies and things like that, and local governments, when you have this huge influx of people. So I just wanted to share that story with you, and part of that with the public concerns. And specifically, we're going to talk about today is the things that Techmar, as a company, we can test for. The chemicals that make the drinking water flammable, the methane, ethane, ethene, and propane. That's done by RSK175, and the chemicals leaching into the groundwater. That's another thing that we can test for potentially using some of our instrumentation. So this is kind of where we come in. Due to increased concern over hydraulic fracturing process and the release of methane and these other chemicals into the local drinking water, there's a need for a fast and accurate way to do this analysis. So we're going to examine a couple of the current methods right now, and then talk about a couple of new methods. So again, how do we test for dissolved gases in water? The current method that has been used is SOP RSK175. It's an EPA SOP. It actually has a title, Sample Preparation and Calculations for Dissolved Gas Analysis in Water Samples Using GC Headspace Equilibration Technique. So like I said, it's just an SOP. It doesn't really go into the detail of, if you know EPA approved methods, there's not been the full gamut of testing that those methods usually undergo. It's not an approved method. It can be used for a variety of analytes: hydrogen, methane, light hydrocarbons, nitrogen, nitrous oxide, and oxygen. We're going to concentrate here in our methods that we're going to examine today in the methane, ethane, and propane. But it can be used for any of these dissolved gases. There are some drawbacks to doing this, since it isn't really standardized. There's not a whole lot of guidance on standard prep, calibration, things that are normally in an EPA method. They're just not there. They're kind of it's kind of left up to you from lab to lab, and labs have written their own SOPs pretty much on how to do this analysis. And we kind of saw that when we were trying to do the front work on this, that there wasn't a whole lot of people that were doing this exactly the same way. So it made it a little bit difficult to find out exactly what you're dealing with when everybody does it differently. I mean, everybody's doing this analysis, but there just was so many different ways even to do the standard prep that it kind of made it, we kind of had to focus in on one area and kind of go with it. And this is what, has been implied since we started with hydraulic fracturing. This has been the method that everybody uses. Everybody uses RSK175 or a variation of it to do the light hydrocarbon in drinking water. And we're gonna outline the procedure. What's the next step here? Procedure actually involves taking anything. It doesn't really specify. I think it says a 60 mil volumetric flask, or not a volumetric, a VOA vial, and then you extract 10% of the volume, you push it out with helium, you shake the vial for 5 minutes, and then you allowing that, if you're familiar with headspace, you allow the headspace to equilibrate, and then you pull an aliquot of that headspace and inject it directly onto your GC. It's compatible with all these different detectors, FID, TCD, and ECD. But along with that, you have some issues with it, because if you are familiar with the EPA methodology for most of the drinking water stuff, there's not a whole lot of sample manipulation. There's not a lot of sample prep involved. You're handling every single sample, and you're doing a lot with every single sample. You're actually doing the extraction in the vial, so that can take a lot of time to do, and manpower. Actually, the response you get is back calculated using, this is a lot of the actual SOP, is the calculations on how you get your gas concentrations based on your response on your GC. But it takes into account the headspace, the volume, the temperature, to determine what the actual concentration, the end concentration is. But this is all done by hand. It's all manual. So some areas have kind of taken this and applied it to automation, automated the sample prep and automated the analysis. And one of the first places we saw do that was actually in Pennsylvania, the Department of Environmental Protection. They started getting more and more of these RSK175 types of analysis. So they were starting to get bogged down. It was maybe 1 or 2 a month, or 1 or 2 every so often. I'm kind of paraphrasing how they said it to us. But they started getting more and more of these samples, and it was starting to eat up more and more of their time. So they came up with this, what is the Bureau of Labs 6019. It's an SOP on how to do this analysis, but it is automated. And it, as it says here, it's a modified method that helps simplify and standardize the sample prep and the actual analysis itself. It's just a lot more refined than the general RSK175 is. It kind of helps you to have this method in front of you. You know exactly what you're doing. Everything's set up, standardized, and to the T. So you're ready to go. It employs a headspace analyzer, an automated headspace analyzer. And it uses liquid calibrations, which seem to be more real world. Using a gas standard to make, which some people do in the RSK175 analysis, seems to be a little, there can be a little bit of a disconnect in your response potentially, because you're dealing with liquid versus gas. It just seemed a little bit strange to us to do a calibration in a different matrix than the sample itself. So this was something we wanted to look into on our own. And it does still require sample handling. You do have to take the water from the VOA vial and put it into a headspace vial, but really that's the only sample handling you have. It has calibration requirements, which the SOP RSK175 does not really have. They have set a percent RSD of less than 20%, or an R squared value of greater than 0.995. Those aren't too difficult to get. Calibrations seem to hold pretty well, so not usually too stringent of requirements on this analysis. So, like I said, it still requires sample manipulation. It's a step in the right direction. You have everything standardized, and you're doing it in the same matrix. But again, when you're dealing with the headspace analyzer, you're going to be limited in your sample time. Before, when you're doing it on RSK175, you kind of can just inject and go at your leisure. This, depending on what system you're using, if you have to chlorate for half an hour, you can't run really quicker than half an hour. That's your limiting factor, based on your platen positions and things like that. So if you have a single position platen, you're not going to get any quicker run than potentially 30 minutes. So here we're going to evaluate on our instrumentation here at TechMar, our headspace analyzers, this method, RSK175, and then go through that on our instruments and show that they're valid there, and then see how things turn out. Here's our sort of generic GC parameters, if you will. A lot of these are dependent on the column, really. There's not, I mean, in the column, as you see here, we're using a U-bond column, a 15 meter. There's a lot of different things that'll do this light gas separation. If you can find something, we've had recommendations for a couple different kinds. As long as you can separate out specifically the ethane and ethene, which seem to be the troublesome colluders, if you're looking at those two compounds, the column shouldn't really make a whole lot of difference, to be honest. It's just whatever you can do the separation on. But yeah, this is the one we went with here, the U-bond, and then our oven program is another place where we have some flexibility. We run cycle times anywhere from 6-7 minutes up to 15 minutes. It just depends on the column and your prep method, and if you're running headspace, it might depend on your equilibration time. It's very flexible here, depending on what you need, what exact compounds you're looking for. If you're dealing with ethene and ethane, you might have to make some adjustments to your oven program to get that potential coelution out of there. But other than that, the other three, methane comes out separate from ethane, ethene, and then propane's kind of far off. So it's a pretty easy separation. And if you could just do those three compounds, you could probably even run isothermal up to maybe 150 on this column and get some pretty good results. Okay, and I just want to make one note on the split ratio here. I've seen this run splitless. I haven't seen very many people run up this high of a split ratio, but there's kind of a method to our madness here. When you have those tight windows potentially on some of these compounds, since we're looking at 4 and 5, 6 compounds potentially on this, if you run splitless, your response, if you had 2 of those in the same sample, they're going to overlap no matter what you do. We found 20 to 1 to be a pretty good spot where we got good sensitivity enough to see our low-end calibration, but at the same time we weren't getting the crazy coelutions when we got to the high end, because this is a pretty dynamic range, as you'll see. And we want to try to avoid that coelution problem on FID, because we can't speciate like we can on mass spec. We can't tell what the difference is. It looks like one peak, and for all intents and purposes, it is one peak when they come out like that. So there's not much we can do about that other than try to prevent it. But that kind of helps us. The split ratio is something you can dial in to kind of, based on your compound list, kind of help to optimize your setup. Okay, the next is kind of the general. These are our methods for our headspace analyzers, the HC3 and the Versa. Since it's a loop-only method on the headspace via BOL 6019, it's a headspace or loop-only method. Sorry, you can run it on either instrument. They both have a loop on them, so either one can do it. We wanted to show that we could do it on either one, based on the potential throughput on what you might need to do. If this is something you're only going to need to run 1 or 2 samples or every so often, the Versa, since it has a single position platen and it only has 20 positions, you can get away with using it because you don't need to run that many analyses. But if you need to do a bunch of them, you probably want to look into getting an HG3, because with its multi-position platen, you can prep more than one sample at the same time. So as one comes off, it's running the second one. After your first one, I mean, the equilibration is a limiting factor, but after your first one, since it's already started prepping the second sample, you can get some pretty good cycle times on consecutive samples. It'll get quicker and quicker, and so your actual limiting factor would probably be your GC cycle at that point in time, not your equilibration time. But like I said, the Versa only has a single position platen, so the runtime is limited by that number. And I think for the method, it's 30 minutes, so that's what we use for this validation. Okay, here's our standard prep for the headspace methods. We take a saturated stock solution, which we make by bubbling a gas standard, 100% of whichever constituent, methane, we'll say, and then you bubble it through your water at 0 degrees for an hour, and then you get a concentration based on the saturation point in the water. It's roughly about 40 ppm. So what we do is we take that and we dilute it down to get your different points on your calibration. I'll talk a little bit more in detail on standard prep later when we talk about the purge and trap side. But I just want to make one note that since the saturation points are different for all these gases, you might make the same dilution scheme for all of them, but your concentrations are going to be vastly different, because I think ethene has a saturation that's like in the 270 range, and then methane's like 40. So depending on which gas you're dealing with, your concentrations are going to be potentially widely different, running even the same dilution scheme. So that's something that's a little bit different, and something you need to account for when you set up your standard prep for a headspace method on this. Okay, here's some calibration results. Both instruments perform really well. Remember that you only need 0.995 or above based on BOL 6019. So everything looks good here. Didn't have any real issues running it. It's something we've done this dissolved gas before on our H33 previously with a different prep method using the standard RSK175 method. So this is pretty much just an update of that for that particular instrument. This is the first time we ever ran this on a Versa, and it seemed to perform pretty well. And if you look at these, the range of the calibration, I mean, that's 1,000-fold potentially that you're dealing with on a dynamic range on this analysis, and that's kind of that was part of one of the challenges we had to deal with it. That's a really wide range for a gas type analysis to have to do, and that's where the FID can definitely be very helpful in it, because you don't have to deal with a crazy matrix. You're just burning stuff, so it's not as difficult to do as it would be on maybe a mass spec or something like that. So here's the calibration data, and then we with that we ran MDLs. They're well below the bottom points of the curve. As you can see, the curves back here, it goes anywhere from 20 to 74 on the low end, and then we don't have anything above 25. And the note on that 25, it seems high on the HC3 MDL. It's not that that's really high. It's that the Versa was so tight on the ones that we ran that the 2 ppb is actually unrealistically probably low. It turned out really good, that run of MDLs. But as you can see, if you go back, the bottom end of your curve on ethene is 141 and the MDL is 25. So you're definitely well below. I mean, you're 5 times, almost 6 times lower than your calibration curve. So that's definitely still pretty good. But yeah, it definitely performed very admirably in doing this analysis, and there weren't really real issues running it by headspace. Here's a chromatogram of a mixed standard, and you can see how it will look on an FID. The inset is actually the response on a HC3 and a Versa to kind of overlay and show that there really is no difference. I mean, you're running a loop method, so you would hope that there was no difference. But this just shows here that there is no difference. And now that I have this chromatogram, I can kind of touch on this ethene thing here that we had talked about before. If you look at these guys here, specifically these 2 compounds, depending on how you set up your oven program, these can actually switch positions. So that's something, if you have to analyze for these, I mean, some people don't really have to do ethene. It's kind of from my dealings with some of the regulatory agencies, they don't really see ethene in a lot of their waters that they analyze. But if you have to analyze for it, it's something you got to take into account here. Since you can't, like I said, since you can't speciate here, you need to keep them apart as much as you can, and that's something that the split ratio can help you do. And it's also something you want to keep your oven temperature, your starting temperature, pretty low to keep them separate. If you start to ramp it up to 40, 50 degrees, they start to come on top of each other, and it's really hard to get baseline separation. But it does take some tweaking depending on your method and your column. So this is just an area to be aware of. And potentially, if there's some of the other list compounds that we're talking about, you might be able to do by this. They may or may not collude. So there's going to be some definite optimization based on the GC configuration. So just a note there that while I had a chromatogram up to kind of show that there are potential collusion problems there. So in conclusion, for the headspace analysis, both of them performed the automated RSK175, essentially the BOL 1619, very well. But again, the HC3 will cut down your sample time, your prep time. So if you need the high throughput, that's definitely which way you want to go. But the Versa, it definitely gives you just as good data, quality data. It's just a little bit slower because it only has that one platinum position. So it just depends on your needs. If you need a higher throughput, then that's where you can go. And one of the pluses, you decrease potential variability when you do manual injections. I mean, manual injections on a GC. We're all, some of us are better than others when it comes to doing injections on a GC. But we're not auto samplers. We're not near as good, or I don't think they would have auto samplers. It's just you're going to get better reproducibility using an automated system. It's just the way it is. We met all the performance criteria as we discussed with the .995 and greater than the .995, and the MDLs were definitely looking pretty good. And this is one of the pluses of running it on a headspace. Since you're using standardization using liquids, you're looking exactly like a real world sample. There's no difference between your calibration standard and a real world sample, which is really what you're going after. So it definitely is helpful to do it that way, I think. So that pretty much wraps up the headspace analysis part of this presentation. And now we're going to move to the sort of the new stuff, the purge and trap method development, which is something I've been working on for a little while now. So this actually came from a customer interest, which was kind of, we hadn't really heard that much about the hydraulic fracturing. We'd heard some things in the news, but we didn't really hear anybody trying to test for it using purge and trap. But we had a customer interest that actually kind of pushed things forward and kind of came up to can we even do this by purge and trap? It would have benefits. It could run it straight out of a 40 ml VOA vial. You wouldn't have to handle the samples. So, there's definitely some benefits there, but is it even possible? So we kind of had to start from there. And here I'm going to kind of go through a few of the challenges that we kind of either saw at the time or didn't really see at the time, but I'll kind of go over some of the ones that we kind of had to go over. The trapping material. This was key. With purge and trap, if you can't trap it, what's the point? There's a lot of options here. There was, we were lucky that we had a recommendation from the particular salesperson dealing with this customer, but there was definitely a lot of different places that you could go here. So we had to start there and see if we could even trap it. The dynamic range of this analysis. Low ppb to high, potentially really high ppm levels. The ethene is 270 on the high end of the curve. That's a pretty dynamic range, especially if you're trapping. That can be a challenge. The FID is definitely there to help you, but this is another thing we have to consider when we're going forward, trying to develop a method to do this analysis. And then we have our purge and trap parameters. There's a lot of different considerations. What kind of sample volume do we need? Do we need the sensitivity that a 25 mil gives us? Can we use 5 mils? Is there going to be any benefits or drawbacks to using either volume? The purge volume, this was probably one of the biggest hurdles, because once you have the trap, it's like you have to do pretty much any trapping material. You got to come up with a limit curve on what kind of flow and what kind of time, and so essentially the volume that you need to kind of optimize the trapping of these gases, because they are just so volatile that they're really difficult to deal with potentially. So I ran many limit curves based on some of the other parameters to kind of dial in these the purge volume that we would need to run this method. And then when you start adding the auto sampler, and there's a bunch of other conditions you got to account for. We started off with just the purge and trap concentrator initially to test sort of, is this viable? Can we do it? And then as we do that, we have to automate it, or else you're going to be doing it manually, and you might as well just stick to the normal method. So with the auto sampler, do we need to chill the sample or not? Do we need how cold do we need to keep it, things like that. The sample temperature, as we found out going through this, was actually one of the most vital things that we found. If you can think about it, when you're making a saturated gas standard at 0 degrees, you let that equilibrate to room temperature, and as soon as you pierce that, that's become a supersaturated solution. So, that can lead you to crazy issues with reproducibility. It's just all over the board, and you're not going to get the same thing twice. So that was something that we found out the hard way, sort of when we first ran it and didn't have the recirculating bath hooked up, and it kind of didn't give us consistent results, and we're kind of scratching our heads wondering if it's a trap or anything else. But it turned out to be the sample temperature that was really one of the key things for reproducibility. And then when you have an auto sampler, when you have cleanup potential, you have potential for carryover, so that was something we had to look into. And then you have your GC considerations, because we got to figure out what column we need to use, what kind of oven temperature, the same things we kind of discussed before when we kind of came up with our generic sort of GC run. But then do we need to split the sample, and then what kind of sensitivity do we need to meet the dynamic range at the same time, meet the sensitivity and at the same time still not kill the column or anything like that. I don't want to overload the column, don't want to collude, things like that. So those are all things we had to consider when we were going forward with this, when developing this method. So after some method development, limit curves, all that stuff, this is kind of where we're at now. This is what we found that works really well with our new trap. It's kind of driven by rapid analysis. We want to do things as fast as we can. So that's why we're kind of pushing the envelope on trying to get cycle times down. So keep the samples cold, and really the least amount that you can handle that sample after when you start to sample it, the better. So we've tried to keep we've gone with a 5 ml sample volume to kind of keep all things as cold as possible and do the least amount of sample manipulation that we can, because they found that doing more sample manipulation gives you probably reproducibility. So that definitely is something that we went with moving forward. But nothing. It is kind of a specialized method. Some of these things are kind of off the wall. The bake time is really 15 minutes because of the GC cycle time, because we kind of wanted things to be the same. So there's nothing real crazy on there, but that's kind of one of the things that might poke out to you, going, well, why is the bake time 15 minutes? Is that going to be a problem? We haven't really seen any issues with the trap. It seems to hold up pretty well, even at 400 mils a minute for 15 minutes. But that was more just to get the cycle time the same. And if you look at the bake temperature and the desorb temperature, those are pretty much based on the trap. You don't really need heat to get these things off the trap. Really, flow is your best bet to just even get them off there. So we don't really need a lot of heat. It doesn't really require it. So there's no point in potentially damaging the trap to heat it up real high if that doesn't get you anything other than crazy baseline on your FID. So yeah. So here's our standard prep for our PURGE trap. We made these up in 50 ml volumetric flasks. Again, this is pretty similar to the headspace. We start with the stock standard and dilute it, but it's all made in 50 ml volumetric flasks. So just a standard dilution of a stock standard, and then these are your calculated concentrations based on the saturation points of each gas. So that's pretty straightforward. And now I'll talk about some of the issues that if you're going to do this analysis, these are sort of my my tips that I give to people when they ask me questions about this. Since you're starting, like it reads here, since you're starting with the saturated gas standard, I touched on this earlier. You want to keep it cold throughout, pretty much. When you're making the standard, keep it as cold as possible. When you're handling the standards, try to minimize your amount of movements. Try not to let them sit out too long. Try to keep everything as consistent as you can with your sample prep. I usually keep a liter or two of cold deionized water in the fridge at all times, in case I ever have to do this analysis, just so I don't have to wait. It seems to keep things more reproducible, to have everything cold as possible. It's just you don't ever want to approach room temperature if you want to have consistent results with this analysis. So, like I said, you do dilutions of stock gas standard over dynamic range. It's kind of a wide range, as we said. And then you just take your you just put it in the 40 ml vial, and you set on the auto sampler, and you're good to go. Auto sampler does the majority of the work for you. It keeps everything cold. Try to keep things below 10 degrees. 10 degrees seemed to be a pretty good spot where people could actually achieve and not have any problems with ambient lab air. Our chillers could kind of get there without any issues, so we kind of went with 10 degrees. And then you have, like I've said, you want to try to keep this stuff as cold as possible. There's a couple different dilutions that can be challenging when it comes to keeping things cold. Like if you think about it, one of the, if I go back to the dilution scheme, a 25 mil to 25 mil dilution is kind of tough to do with standard sort of. I mean, for the low end, you use syringes, and those are easy. Those are cake. The 50 mil you just pour directly in. But when you do a 1-to-1, it's like the most amount of transfer time that you have, and transfer time's bad, as we've seen with this. So that was the challenge, is really the 1-to-1, and pretty much anything that involves having to do having to do it. And we tried syringes, like 5 mil, 10 mil syringes. Those are okay. It's just that there's another thing. That's another step that makes it kind of challenging. Is trying to get consistent results on your dilutions. And I've tried putting glassware in the freezer, all sorts of things, try to keep my reproducibility. But that's definitely the challenge with this, is trying to keep your movements as consistent as possible when you make the standards. So just a couple of notes, a couple tips on standard prep. So here's the calibration data that we generated for the purge and trap method. We do a little lower on some of these than they do on the headspace, and that's basically just based on the dilution scheme. Our linearity was excellent. Our RSDs are really, really good at a methane and ethene, and kind of go up a little bit, but I mean, they have to be less than 20. They're definitely well less than 20. But these are kind of tied to the purge parameters we set up. We've kind of optimized it to run methane. As you start to get out towards ethane and propane, these things start to behave more like regular everyday VOCs. So you have a little more trouble getting them out with a quick purge. So the RSDs suffer as a result of that. So they are still well within range. There's really no, this isn't bad data, it's just that I wanted to explain sort of the difference here. We're definitely very optimized from methane and ethene, because they're the quickest ones to come out, and they're the easiest ones to purge out. So we didn't want to lose, we didn't want to kind of have a middle of the road set of purge parameters, because it would probably hurt the methane most of all, because that's really the most volatile, really the most challenging compound on this short list. Okay, so we have MDLs. As you can see, they look really good. The methane is really low. Since we're optimized for methane, it's definitely really reproducible. At the low end, there's no background or anything. It looks great. And all these other ones, ethene through propane, are definitely well below your calibration ranges. So everything looks really good with our MDLs. And then percent carryover, which is something we always have to examine when we're doing purge and trap. They're all, I mean, for most VOC methods, we claim to be less than 0.5%, and these are all like less than, I mean, 0.04 is pretty low. And the funny thing is, when you consider these carryover results being extremely low, they kind of have to be. If you consider the dynamic range, I mean, to generate this carryover study, we do a saturated gas solution, and then we run a blank right after that and see what we get. So you're going from 40 ppm, and then 0.04% of that. I mean, that's still in your working range potentially. So you have to be really low on your carryover. It's going to really hurt this analysis because specifically the dynamic range. It's just so high that we're running a carryover study on, that you hope that you can get a workable reporting limit out of that. And it seems that we can get pretty good reporting limits out of this analysis. So the carryover is really low, which is good. And here's a chromatogram. This is an overlay chromatogram for the PURGE and trap analysis. And as you can see, there's no coelutions. And you notice the propane starts to tail. The propane starts to tail a little bit. That is basically just because of the oven program. This column that we used, if we could ideally in a perfect world run isocratic at 150 or 100, these peaks look great. They're perfectly Gaussian. There's no problems. But then again, we get the ethane coelution. So we kind of go with this. The chromatography doesn't look so great on propane. It definitely doesn't do so good. Or it looks more tailing as it gets higher in concentration. But it's still reproducible, and that might also contribute some to the RSD being a little bit high, but not high, but a little bit higher than the others. But it still works really well. And then here's our conclusions on the PURGE and trap side. We have very little that we have to change from our current instrumentation to run this analysis, and that's definitely a benefit. We really just have to change the trap, the column, and if you don't already have one, you just need to add a recirculating bath to your instrument now, and then you're pretty much good to go. There's other things you have to order, potentially order standards and things like that, but as far as our instrumentation is concerned, this is just a swap out and you can run. It's really, really simple. You get the same advantages that you running the automated headspace, but you also get the fact that you're running in a 40 ml VO vial, self-contained, no manipulation of sample, no sample prep. Once you have a calibration curve, really, you just have to run your CCs, your cal checks, and then you're good to go. You don't really have to make up any samples, and it makes life a lot easier. Yeah, that's underlined. No need to manipulate samples. They seem to really like that in some of the places that we've instituted this analysis. They can kind of just set it up and let it go. And it has the potential for fastest run times and highest throughput of all the methods because you have no equilibration time, and you're not really. If you can get your GC cycle time down based on your column, you can run as fast as you want. I mean, our purge time, if you go back and look, it was. I mean, our cycle time on purge and trap was maybe 4 minutes, 5 minutes at the most. So you can pretty much turn these out in 6-7 minutes, and you can get a lot of them done really quickly if you have the capability to do so. So really, there's really nothing that compares to it as far as how quick you can get things off of here. It just takes a little bit of optimization on the GC side to kind of go that way, but messing with the GC and shortening the runtime doesn't really affect the chromatography as long as you keep everything with baseline resolution. Everything, when we ran 6-7 minute cycle times up to 15, everything looked really good. And then, like I said, GC cycle time is a limiting factor, and if you do too fast, this is a word of warning, you will get coelutions depending on what you're dealing with, so just keep that in mind. I just wanted to make one acknowledgement. We've worked extensively with the Pennsylvania Department of Environmental Protection to do this method development. They've been really helpful in getting us set up with their method, BOL 6019, and working with us on developing this PURGE and trap method. And their advice has been definitely really helpful in getting things going with this method. And we just wanted to show our appreciation for their help on this method. Here are some references that we use to kind of come up with this is where I got all the slides on the actual method itself. Fracfocus.org is actually serving as a template for registering well sites and chemical disclosure for the entire country. So it is definitely a good resource to use if you're interested in this. It'll tell you all the registered well sites in North America. It goes through all the different chemicals and constituents in the fracking fluid and all that sort of thing. So these are some good references if you're interested in doing some more research on this sort of application. Okay, that's the end of this presentation on RSK175. I'd like to thank everybody for their attention and participation.